Okay, so is there anything anybody wants to ask from this, or I'll discuss the second case? Okay, so the second case is that of a constant magnetic field, right? And again, let's say I restrict my magnetic field, constant magnetic field. Let's say its magnitude is B, and I can choose it to be along the Z direction. Now, the Lorentz force, or the expression for equation of motion, reduces to E by C V cross B. Right? Now you must understand the way magnetic field exerts force on the charged particle is that it's not going to affect its motion at all along the direction parallel to the magnetic field, right? So motion along Z direction, clearly, one can, in fact, just from very simple logic, will understand that that motion along X direction, if I solve for it, because it will not be affected by my magnetic force or my magnetic field, is going to be just a straight line, right? As we know, there is no, it's not, I mean, if the charged particle is moving without any external force, it's going to move along a straight line, right? So I can write from here, hence, my Px and Py, and I can again use that relation between P and E and V. That is my energy, my velocity, and momentum. Put it here for P dot and write down for Vx dot. Let me not skip any step. I can substitute it here, write this as E dV by dt, E by C, V cross B. Right? Then I can write X direction. X component of this will be E by C square. That's the energy by C square. Vx dot equal to E by C, X component of V cross B. Right? X component of V cross B will be Vy Bz minus Bz By. There is no By. So this is E by C By B. Right? Or Vx dot becomes ECB by I have to keep adding people in between. That's a real distraction. I can write Vx dot and ECB by E times Vy. Let's call this total energy, magnetic field, CE as some omega. So what is this omega? We'll see what this omega is really later on. What is its physical significance? For the time being, it's a parameter that I define like this. And now it is not difficult for you to write Vy dot. Vy dot will turn out to be omega Vx. by component Bz Bx minus Vx Bz. There is no Bx. So only term that is finite on the right hand side is minus Vx Bz, which is minus Vxb. And I just rewrite. So I have equation 1, equation 2. Now I need to combine. You can see that there must be a way to combine these two equations. The way they look like, there should, and third equation, let me write that also. Vz equal to, Vz dot equal to 0, right? Because there's no Z component here on the right hand side. Okay, so there's a trick to add equation 1 and 2. What you can do is that you multiply 2 by an iota. Let's call this as 2 prime. And add the two equations. This iota is going to help us. So I write my left hand side as d by dt of Vx plus iota Vy. Now look at the right hand side. I have minus iota omega Vx here and then omega Vy here. I can take out minus iota omega. If I do that, this is going to give me Vx. And that's going to give me plus. That's going to give me plus iota Vy, which is exactly what I have on my left hand side. Now this solution is not difficult. You can just integrate this equation. And when you integrate it, you will get some A times, where this A in general is some complex number. Constant of integration, we can determine it from our initial conditions. But there's a nice way to rewrite this equation. So since this is a complex number, I can always write this complex number as some magnitude. I'm writing it as some V naught t because you must see that it will have dimensions of velocity. E to the power minus I phi. A real part is its magnitude and a complex number, a complex part. So let's say if I write it like this, this equation becomes, now this is a real, this is magnitude. So I can write this as cos omega t plus phi plus iota V naught t sin omega t plus phi. You can determine V naught t and phi from your initial conditions. You will have two initial conditions. You will have one in terms of velocity, one in terms of position. You can always determine, but you can also see what V naught t is. You can see if you compare left hand side and right hand side of this equation, you get your Vx as V naught t cos omega t plus phi. You get your Vy as V naught t sin omega t plus phi. So that tells you V naught t square is Vx square plus Vy square. So now you can determine your V naught T and your phi in terms of your Vx and Vy. And then you can use your initial condition and determine your quantities. I'm not going to do that. I'm not interested in that. Let's keep that for the end and determine the constants, all constants of integration in the end. Right? Now, once I have this and the third equation, we should not leave that equation. And that equation was that Vz dot was 0. So Vz is a constant. Let's call it V naught. Let's integrate once more to get xt. You do the integration, xt will be some constant plus V naught T by omega. I'm doing integration and I get sine omega T plus phi. I call this quantity V naught T by omega as some R. So I get R omega T. Similarly, I'll get my Yt as some Y naught plus R cos T plus phi. And I have my Z as what? Z naught plus V naught Zt. So I have these three parametric equations. It is really nice to put these three parametric equations together. You know what the result is. I can combine this and this very easily into what is this? This is equation of a circle with this radius r. You can actually see what this radius r is going to depend upon. This radius r is your V naught T by omega, which is, if you just substitute for everything, you can actually write, okay, we can write this as V naught T E C E B. Right? You have seen this expression. How? Is that you can rewrite this as some C square should be there. This should be C square and then C. This is some kind of momentum. I'm sure you have seen the same expression in your classical electricity magnetism class. So this is equation of a circle which is moving along the z direction. Right? So this motion is nothing but a helix. Right? So you have the particle executing a circle in xy plane, but is also moving linearly along the z direction. Right? This is exactly what you must have studied in your electricity magnetism class in your first year, right? It's just that you have to remember that now all your expressions here, this P naught T here. So you would have defined something similar, a similar radius in your electricity magnetism class in your first year. It's just that now you have to remember here, this expression for P naught T is not an expression for which is equal to some m into v, but is some relativistic momentum, right? you can actually reduce this expression to your classic. You don't have to do anything else here. The expression is so simple. You just have to look what R is in relativist, is in Newtonian limit. Is you just have to substitute for your expression for, in this case, energy as your rest energy and your momentum as just mass into velocity. And you will realize that that omega that I had in the beginning is something similar to what you must have seen as the frequency, what you must have done in your classical electricity magnetism class, using it as some kind of frequency or the rate at which it goes in the circle, right? It's just that you realize here, when you do the whole idea in classical electricity, when you do classical electromagnetic theory, electricity magnetism, there you write down an expression for current. You assume the charge particle going in a circle. You write down an expression for current. I don't know how you did it, but there are ways to do it. One way to do it is that you write down corresponding to it the fact that charge particle has a certain motion, and you balance out forces in that case. Here, I have not done anything. I have just started with my equation of motion, right? And I have arrived at my expression for the trajectory, and it is going to reduce to what you have seen in your classical class, right? So I'm going to stop here, and now I want you to do the third case, is where you have both electric and magnetic fields, right? In fact, third case can be split up into two parts. First part can be where electric field and magnetic field are, let's say, parallel to each other. And third case, where electric field and magnetic field are perpendicular to each other. You know, in this case, electric field and magnetic field perpendicular to each other, the motion is a cycloid, right? You should be able to deduce first from your expression that motion is a cycloid. It will be easier for you to see that it's a cycloid when you will take Newtonian limit of your relativistic expressions, right? So I can wait for 2-3 minutes if somebody wants to ask anything, or else we'll continue. We'll finish this. So I'm not going to do this. Otherwise, in the next class, I would like you to do this on your own. So in the next class, now I'm going to just wind up classical charge particle electrodynamics by defining the electromagnetic field tensor, right? That's the last part that I want to do in this section. And then, so this week, next two days, I'm going to just finish this one, right? But I would insist that you do this. And if you face any problem, you should not face any problem. If you face any problem, we can then do it later on. So we have 2 questions from the previous tute sheet pending. I'm going to add 2 or 3 more questions to the tutorial sheet, right? And then tomorrow I'm going to finish this first, and then Friday we'll do the tutorial. We'll finish the tutorial sheet, right? So, is there anything anybody wants to ask at this point? Okay, so then see you all tomorrow. Please try to finish this and let me know if you face any problem, right? Okay.
Thank you.